Bruno Sanchez. I'm very thankful for the invitation to be here. The conference seems to be an exciting week, and the place is amazing as well. So I'm here to talk to you about this exciting project that I'm part of, which is the Vera Rubin Observatory Legacy Survey of Space and Time. As I said, I'm a member of the data management team, basically the group of people that are building the software, which is one of the key components. I did forget to mention I'm a postdoc at the CPPM lab in Marseille, in part of the CNRS here in France. And I'm in strong collaboration and tight collaboration with people that work for Rubin, funded by the NSF and the OE. So, this works. Yes, I want to just to briefly take a minute to mention the amazing Vera Rubin. She is the observatory takes her name because we want to honor her legacy. She was a strong scientific contributor with first evidence and strong evidence for the existence of dark matter. But more importantly as well, she was an advocate for women in astronomy, and she given her weight in the scientific community, being able to for her to amplify voices of other people is a very strong thing. And this is the first big survey observatory named after a woman. And we also want to say to people that in papers and talks, please don't use the VRO summary of the name, so we can honor her. Okay, so an outline of what I'm going to talk to you about. I'm going to introduce the observatory itself and then the survey that is going to be conducted during the first 10 years of operation of this new observatory. I'm going to mention the components of the survey and how we're going to deliver data, which is a key part for this workshop. We're going to talk about the alert distribution, which is, I think, of interest to many of you in the audience. And then I'm going to take a tour for the, for showing what has been done in the commissioning and the beginning of operations of this new observatory. Right. So to establish a bit what I'm, be going to referring all the time. So this is the Vera Rubin Observatory. It's finished construction this past week. So we're happy to say that it's a large aperture wide field ground-based optical observatory, located in Chile, and it contains key pieces of technology and new designs that we think are going to enable amazing science and discovery. One of them is the telescope. It's an 8-meter class telescope, first of its kind. The camera, which is a 3.2 gigapixel camera with a very high resolution, covers all the spectrum of the optical to infrared, and then the automated data processing system, which we think as well takes a huge effort from the team, and it's a very important component. So like I said, it's located in Cerro Pachón in Chile, in the 4th region near La Serena. This is a site operated by NOAA and AURA, the associations of the University for Astronomy Research, and near the observatory as well, there are other instrumentation that is operated by AURA, the SOAR, Astrophysics Research Telescope, and then Gemini South, which is an 8-meter telescope. And then as well, here you can see in the mountain, the Rubin Auxiliary Telescope over there, which is a 1-meter class telescope dedicated to provide telemetry on the atmospheric conditions in real time to Vera Rubin. So we can provide calibrated information to the community almost in real time. So how did Vera Rubin happen? So the project started by thinking about these 4 main science drivers. One of them is the energy and matter contents of the universe. So probing dark matter, probing dark energy, understanding these exotic and unknown components of our universe. Rubin is going to provide 20 billion galaxies with accurate photometry and position and measurements of shape of these objects. Then we're going to map the Milky Way. The aim was to measure all the stars of the halo, possibly find out what was the formation of the Milky Way process. And for this, we're going to provide 17 billion measurements of stars. There's also an inventory of the solar system there's a survey, part of the survey is dedicated to the ecliptic in order to find near Earth objects, and for planetary defense and for understanding formation mechanisms. And then finally, which I think is of great interest to everyone in this room, we're gonna conduct a survey that is a time domain survey. And it's gonna explore the transient sky. It's gonna try to fill in the variability phase space of very dim and very quick objects. And we are gonna deliver alerts every night of everything that we have seen. Roughly, we expect the order of magnitude of 10 million alerts per night. So, given this mission, we understood that we needed a very wide field of view, something that could move very fast and reposition itself in the sky quickly to cover more area. And we wanted for each image to be very, very deep and to be able to image faint objects. So when you combine all of these, basically the project aim to create the greatest astronomical movie of all time. So covering the entire sky at the very deep magnitudes. So in order to achieve this, key technological components have been developed, and Rubin has pushed the limits on many of the areas. Like I mentioned earlier, it's the camera, the largest ever camera built for astronomy with 3.2 gigapixels. The telescope, which is a 3-mirror design, is extremely fast in its slew and repositioning with excellent image quality in a wide field of view. And then the management system, the data management system, which enables quick processing of these monstrous camera images. Quickly going to the camera, like I said, it's the largest camera ever built. We have a 10 square degree field of view of usable information. This is roughly 45 times the size of the moon. This is organized in 189 detectors. And we also have 6 band passes, U, G, R, I, Z, and Y, which as well are record breaking instrumentation for astronomy. These are the largest ever built filters for astronomy. So 75 centimeters in diameter. This camera is extremely fast as well for readout. It can be read out in 2 seconds. It has 32 individual electronic amplifiers that can read this camera. Every CCD is packed into rafts of 3 by 3 with the supporting electronics and the cooling. It's a camera that weighs 3 tons because the cooling is integrated completely in the focal plane. And and it was shipped to the site earlier in 2025, and we can say now that it's in working conditions. So you can see the scale of this is roughly the size of a car, and moving it to Chile was a very delicate process from SLAC, where it was built. All right. The second component of this awesome new instrument is its telescope. It's like I said, 2-in-1, primary and tertiary mirror. It's a 3-surface configuration. It's called Paul Baker. It's a modified version of a Paul Baker, and it has a very large aperture of 8 meters. And then the tertiary mirror is carved into the same glass. So we have a 8-meter primary mirror with a 5-meter different curvature surface on it, and then a secondary mirror here. These are the 3 lenses that are inside in the camera housing and as well cooled. And these are, as well, are the largest lenses ever built for astronomy. So it's a very, very innovative system. So a Paul Baker configuration enables you to have a very wide field of view with excellent image conditions, and as well a very, very compact telescope. If you think, for comparison, a Blanco telescope for dark energy survey, the DES, it's a 4-meter telescope with almost 6 meters tall. Ours is 8 meters wide in aperture, but only 5 meters tall. So it's a very compact, almost like a lantern thing that you can really slew fast in the sky and provide atmospheric dominated seeing images. So the image quality of the system is almost 0.7 arc seconds in resolution. So all of this because we needed something called attenuation. Attenuation is the main parameter that you want to characterize of your system if you want to cover a wide field of the sky very quickly. And LSST is 1 order of magnitude larger in NetNU than any other survey instruments before. It's basically the product of the light collecting area, which is for us is 8 meters in diameter, and the field of view. And if also you combine this information with the density of pixels, you have LSST here being the first instrument to achieve this type of metric value. This is a picture of the system that was taken during this year in the dome, where we have the new calibration screen. This is basically for taking dome flats. And here are the different colors. These are we're taking with a Google Pixel phone inside the dome while performing image acquisition for flat imaging. So you can see here all the cooling lines of the camera and all the systems that are wrapped into the mount assembly. I wanted to show you the internal reflections of the telescope itself. Here you can see one engineer in the summit that snapped a picture. He's kind of near the aperture of the telescope, and you can see this is the primary mirror here, the tertiary, and then reflections of the secondary here, and then the camera housing. So it's a very trippy instrument to be nearby, people say. So yeah, it's a very nice telescope. So, like I said, LSST is going to be conducted over the next 10 years, and we're going to be snapping images every 40 seconds with this massive camera. And the main idea is to provide alerts to everyone. So how do we do that? So there's a fiber specifically built for Rubin, optic fiber network. This was laid out a few years ago already. That goes from Santiago, from La Serena to Santiago, and then using 2 channels goes to SLAC. This is the Stanford Data Processing Center, the US Data Facility, that's how we call it, where we're going to process the almost real-time survey, which is enabling the alerts. Later on, some of the images and data are going to be transferred after the embargo, which is 80 hours after finishing construction. So right now, it's 80 hours to the France Data Facility at CC Lyon, and then at the UK Data Facility for further processing and data release production. So this is a massive network. It's extremely fast. This was one of the first things that we tested, and it works very well. So roughly 20 terabytes of data every night are going to be generated. And after the 10 years, this is 500 petabytes. All of the processing is being conducted by what we call the LSST science pipelines, or more familiarly, the DM stack or the stack. It's basically a collection of open source packages and projects that can be reused for any observatory, actually. You can use this code. This is in GitHub, in the LSST, hosted in the LSST organization. And we have code to create catalogs, analyze images, perform image subtraction, for instance, publish the alerts. So there's a lot of work being dedicated into this massive software project with a lot of testing and good practices and documentation to enable this, which is the legacy survey of space and time. LSST is, like I said, scheduling the first years of our Vera Rubin operations. It's comprised of many surveys. The most important and largest is the Wide-FAST program. This is basically covering the almost entire southern hemisphere sky, roughly 18 square degrees, repeatedly during these 10 years. So basically every 3 nights, we image the entire sky in the 6 band passes. And we expect to reach almost 800 visits in very uniform coverage in this area, with some specific deep drilling fields, which have many more images. The magnitude depth expected, for instance, in R1 27. So this is what accounts for the 20 billion galaxies and 17 billion galaxies stars estimates. It's actually an ensemble of surveys. There are more than one. The DDFs is the other main dedication, with almost 7% of the time. These are tiny fields, these yellow ones, that we're going to be imaging more frequently and with many more visits. So we can capture fainter objects and also quick variability. There's also as well mini and micro surveys. There are surveys designed for finding asteroids. The Twilight survey. We're gonna image the ecliptic, the plane, different dusty and not dusty areas of the Milky Way. So it also covers some time. And then the target opportunity. There's gonna be a target of opportunity program that we have been testing during this commissioning phase. And with the idea of being able to stop operations and move fast to a high priority target, a very time sensitive like kilonovae, gravitational wave counterparts, and so on. And we have the software to do this as well. So this is the latest baseline. I can talk more about that later. So how are we going to deliver the data? So it has two answers. The first one is the alerts. So there's going to be almost real-time processing of the images that it's going to deliver data in the form of alerts. The design latency is 60 seconds for these alerts. These are alert packets, but they're going to go to the brokers like Think or Laser, or there are 7 actually. And then there's a 24-hour time to also deliver catalogs and prompt products, and an 80-hour time to actually access the images, the big images, not the cutouts. There's also as well data release products. So every 1 year, we're going to be reprocessing the entire history of observations and obtain catalogs, multi-band catalogs of the images, co-added images, and so on. And these are the data releases. There are 10 scheduled data releases to happen. All of these can be accessed, like I said, through the brokers or in the Rubin Science platform. I don't know if you know about this, but we have built a platform that is enabling scientists to access the data in 3 different aspects. So this is a snapshot of the website where you can log in and start looking at Rubin data. There's a portal aspect. The first one is basically a graphical user interface. There's no need to know coding and to do any software developing for using this. It's basically enabling browsing of data sets, doing interactive plots, exploring the data, finding and so on images. It uses the IBOA standards, so it would accommodate to any of the already known tools that you may use already. There's also the notebook aspect. This is basically a Jupyter notebook interface that enables you to do computing. It's almost entirely based on Python, and you can install your packages, do your own processing, basically bringing the code next to the data for you to obtain information out of Rubin images. And then finally, there's an ensemble of APIs that enable table access protocol, image access protocol. And basically, you can use the jQuery or whatever type of query you like to use in Gaia, for instance, IBO, and so on. Everything is supported. Not only the scientists are going to be able to access the data, Rubin also funds and operates a group that's dedicated to outreach, to creating courses, to providing websites that are friendly for people who are not scientists, and to do as well citizen science. So be on the lookout for this. And I wanted to basically pause right here. And so I've rushed through all the features of Rubin. Now I'm gonna get into what I think is the most relevant topic here right now in this workshop, which is the changing sky, and something that I also dedicate my work. Before talking about the commissioning and the details about that. So I specialize, like I said in my intro slide, on difference image analysis. So basically, whenever you take a new image on the sky, you can, I think all of you know this, you can equalize the properties of this new image with archival good quality images that you already have in your spinning disks, and create a difference of these and detect everything that changed in brightness or also moved and so on. So the main idea is to have a pipeline that's continuously doing this differentiation and obtaining the candidates and sending these to the community. Or getting more technical, our algorithm of preference and our use is alarluptum, which is from the 2000s. You can read all about the implementation that we use in the technical note 021. It's a decorrelated version that basically performs all of these, you have a deep coad image that represents a static sky. You have a freshly taken image. You perform some transform on the template image, and then obtain this difference. Everything that we measure in this difference image analysis, we're gonna, like I said, publish it, and you can find about the schemas in the schema browser. There's a nice document and website for you to find out what information are we publishing actually, and in what format, and what does it mean, each quantity that we publish. And the main idea of sending alerts is basically to provide not only the alert of the position and what exactly, where exactly is it, but also context in this discovery, like basically cutouts with the stamps of the image at the location of the detection. We call these detections DIS sources, and we call ensemble of these detections that are associated in position, that are close to as DI objects, and also the solar system object records. And we provide association with all of these, 12 months of history when available, to send a light curve with information on the magnitude of the object before. Also time series features calculated on these light curves, and cross matches to different catalogs. So the main idea is to provide the community with something good enough for them to do follow up and to basically cross match with databases. So I keep saying that we're going to produce millions of alerts every night, and we're going to send them to scientists. But of course, they're not going to receive that in their laptops. I think all of you know this. This is a workshop of basically a broker. But we're going to publish this through 7 already selected brokers. These are the ones, Alerci, Ampel, Antares, Babamule, Think, Laser, with Google. And the main idea is you can also create your own broker if you want, like Astro-COLIBRI, for instance, and connect to the streams that each one of these brokers is providing as well. So these are the entry points, and they also provide with additional quantities. And you can also get more information from these brokers as well. Okay, so moving from the alerts now to the initial observations conducted at the observatory. We started the commissioning of the whole system using a small camera, the LSST ComCam, that's how we call it. And it's basically full hardware. It looks the same in the outside, or very similar to the true LSST camera, but only contains one raft. This is 9 CCDs at the center of the camera, and we also used only filter exchanger with only 3 filters. Everything else was very similar, like the resolution and the readout. The electronics are the same, so we could conduct a lot of testing already with this camera before mounting the big LSST camera. Here I'm showing you images from the first night and the last night of commissioning. These were taken with ComCam, like I said. And there was a period from October, 1 year ago, to 11 December 2024, where we have conducted a mini survey on 7 specific fields. These are the coverage, 47 to Pene. I'm going to show a map later, where we observed in different filters, achieved the same rate of acquisition as LSST. So this was one of the big challenges for the team. Also achieved 0.7 arc-second resolution. So we achieved the lowest seeing possible already. So demonstrated that capability, and tested as well all the data management. So this is something that you can read about in the technical note 149 for system and integration. And we released this data set as the form of the data preview #1. So this is the paper here. Also, it's a technical note from Rubin 095, where you can read about the almost 1,800 visits that we published from this camera, covering roughly 15 square degrees, the size of it, but also a lot of the scientific performance measurements on these images. So the coverage, like I said, is only in 7 fields. We had fields that overlapped, for instance, the extended Chandra Deep Field South, the Euclid Deep Field South, a very high stellar density globular cluster, and so on and so forth. So this is all published, and it enabled integration of the full testing of the system, at the summit, but also the pipelines. So you can see in the paper as well, some hints about the other production performance. we could do this because there is temporal coverage. Some of these fields, like I said, were covered more than once. So you could potentially build a light curve from images from COMCAM. Here I'm showing you basically the number of epochs per field. Some of them don't have as many epochs, but some of them, like the Rubin SV, contains a lot of images that you can use them for a light curve. This is part of my work specifically, but in order to test the Euler production and difference imaging technique, we injected artificial sources. So basically, we injected stars in these images, almost 1.5 million of these stars, and tested what we want what we have as a requirement, which is the completeness. We want to find them all as a function of the signal to noise ratio of the pixels of the image. After 5, we want to find, and we achieved this. So this is a very important test for us. This is an example random portion of the image. They are not free of artifacts. There are bright stars and artifacts that really pop up, but you know, this is true in every DIA processing. But we could find most of the transients that we injected. Here I'm showing you the photometric, on the left, a photometric estimation of performance, which is the difference in magnitude as measured in the images versus the true magnitude of the injection. So we are basically comparing how are we recovering the brightness. And we also have two samples. We have the yellow sample, which is hosted into galaxies, and then the black sample of randomly located transients. We could find very good agreement with the photometry. There's a difference between the hosted and hostless, but this is within specs. And then on the right, I'm showing you astrometric precision. So basically the residual in the position of the injections with the hope of finding a very centrally distributed residual. And yeah, that's what we find. The dispersion is roughly 0.02 arc seconds and is symmetrical in both axes. So we are confident that we are doing that right as well. This sample of injections also was used for training the real bogus model. So this is a machine learning model that's basically classifying every detection from the possibility of being an artifact of the subtraction and a real object. And it was initially trained on full simulation data and then refined on the LSST COMCAM. And we have achieved very good performance metrics. And this is now under further refinement using the LSST CAM images, which is completely, it's a much larger size of a task. You can read all about this in the DP1 website as well. So you can find information about what we released, and you can cite as well this document. Of course, I introduced the Rubin Science platform because you can, and DP1 because you can basically use the platform to find everything in DP1, all the images and the catalogs. And this is the first and most important resource for you to find out how Rubin data would look like. If you have questions, you're all invited. I think some people actually participate a lot. This is a Rubin community forum where you can just type in your question or browse in past answer questions. And people in Rubin project are in charge of answering. They have to. So there's always some feedback coming from the project for your demands. All right. Then, so COMCAM went down in December. We took it out, and it's not gonna be used anymore, sadly. But it's because we mounted the main camera. This was in the 15th of April, next to my birthday. So I was really happy when I heard the news and saw it. I'm here showing you a video of the, well, if internet and Jeff Bezos wants, yes. So you can see how this 3-ton large camera that it actually looks like a Nikon camera was mounted in the telescope. The clearance is about a few millimeters on the tube of the telescope. So this took several hours and several engineers looking at the, you know, as the movement progressed. But everything inside the summit is like this, is super challenging because it's a dangerous place, it's very high, and everything is big. So if you want to really mount the camera, you have to make space for that. So planning a movement like this took months, and it took a few days of work. So when you see the schedule moving, it's really complicated. So it's not that they don't want to do it. And this camera was mounted, and then on June, I think everyone saw this, we revealed the first images. I like to do this doing zoom out. It's my favorite to do this. So I always try to focus on one object and then continuously zoom out to see the very wide field of view of Rubin. So keep in mind, I'm looking at these galaxies next to these ones. And if we continue zooming out, you can see roughly this is 1.4 field of views of Rubin. And you saw the resolution that we are achieving on those images and how wide they are. This is amazing to me. We have measured everything here, and we have roughly 10 million galaxies in these two images. So this is 0.05% of what we are going to measure. And it's amazing the quality, the color of these galaxies. The team spent countless hours on looking at the color gradients, for instance, because when you see a color gradient, you know it's fake. Then when you really achieve good image quality and coating of the different bandpasses, and you see the profiles changing in color very naturally, then you know you're doing it right. And this is a very hard challenge. But the images look stunning. And so after doing all this work, doing the press release, the team dedicated to what's the on-sky commissioning campaign with the true camera. This happened this last summer, so winter in Chile. There was a lot of complications due to that as well. It was a very strong winter over there. And observations, well, this is roughly the timeline. The start of the pilot survey was on June 20th, and then it finished the 21st of September. So it's already finished. There were many things in between that happened. Some of the survey targets were changed. Initially, it was planned to achieve a very wide area. So do you remember in DP1 I mentioned it was only 7 fields, but now the team was trying to conduct a full simulation of LSST survey in a very wide area. So this required the telescope to sweep over the sky. That was the main target. So a lot of inspiration from the LSST survey observing strategy was taken to define the scheduling. And sadly, engineering and bad weather forced the team to change that plan. So we, in the end, decided to do less visits. So the area originally was going to be 3,000 square degrees, and we achieved only 750 square degrees, which is this yellow area here. And instead of having hundreds of visits, like here, 150, we were able to collect as much as 70 in some of the fields. As well, we put priority into the G, R, and I, and Z band passes, so you can see how the visits in U and Y are not really that numerous, and the depth achieved. Anyway, using this data, which is not small, it might be deceiving how I phrased it, but this is a huge data set. We were able to determine that we are in this area of this performance chart. This is basically the system contribution to the delivered seeing, so the sharpness of our images, and then the effective survey speeds. So basically how quickly we're sweeping the sky. This is the nominal performance designed for Rubin, and the gray box is basically the minimum requirements to achieve the science, and the green box is basically the desired performance for the full survey. Then there's a range of demonstrated performance that we've achieved. This is the orange box, and we know and we have ways of achieving the full performance. This is fine. There's no risk for the survey. I think this is the takeaway. Okay, so right now the observatory is finishing a 1-month shutdown after September, where the camera stopped taking observations. There's a lot of engineering being conducted. Observations were not taken because there was a review to try to finish and declare the finish of the construction, which was, I think it happened last week. So now we have a fully functional observatory. Still a lot of work. to do on making the system achieve the full design specs performance, but we're going to start observations this week. So we're going to begin again taking data, not the same as starting the LSST, which is scheduled to start before the end of the year, for sure. Also, this is important for the community to know. We have understood much better how our pipelines work and how much effort and time it takes. So we have decided that we wanted to, initially, there was a conceived 6-month release of the first year of LSST survey that we are not going to be doing anymore. We decided that the team decided that it was overambitious and it was also jeopardizing the first year release, which we think is much more important. It's not a preview. The first year release for a lot of the science that we want to do in LSST is key. We want to do science after the first year. So instead, we're going to release DP2, which is a new designation for the science verification survey that I just told you about as a form of our release. So this is a new schedule. We are here. We saw DP1 already in June, where you can find the images, the processed catalogs, the different image analysis catalogs, and so on. And then we're going to put out a DP2, which is the science validation data as a form of our release. This will be the last release before the actual year 1 of year 1, which is happening in October, February 2027, 2028. Right, I don't know how am I in time. I did super quickly. Alerts and prompt products are going to be starting to roll out very soon. We are doing a lot of work with the brokers because this is also a huge task for the broker systems to be able to cope with the data stream. We are going to slowly ramp up observations these following weeks and hopefully send alerts. The main idea is to do alerts as a best effort basis, because we need historical template images to do the subtraction. This is a requirement, and the main idea is to slowly increase the rate of alerts until the beginning and the mid-survey phase. Right, so I leave here my conclusions. I went a bit too fast. You can ask questions. Basically, we know we're gonna produce a huge data set that's gonna do a revolution for many areas of astronomy and cosmology. There's also gonna be a world stream of data, world public, for people to do follow-up and really discover new things that we haven't seen before. And after that, as well, we're gonna release huge data sets for the community to dive into and produce more discoveries in science. So stay tuned, because the dawn of the LSST alerts is pretty much coming this year. Thank you so much.